Today I have something pretty interesting for you. We're going to talk a little bit about all those digital images you look at on the internet or from your digital camera. And if you think about it, all those images, really they have to become a group of numbers. That's the only way your computer actually works. So you don't think about it like that, but they actually are just a set of numbers. And not only that, but they have fancy ways of making these files smaller, because the truth is, if you just did it naively, the files would be very, very large. And I actually brought some images with me to show you what I'm talking about. And I'll show you a little bit of the clever math involved in making these file sizes smaller so we can actually deal with them. So for example, I have a full resolution photo on my laptop. Our photographic model, by the way, is Miss Pickles. And Miss Pickles here is at full resolution, meaning what's happening here. And in fact, actually watch, if I zoom in here, you can start to see individual pixels. So as we get closer and closer, you're going to see individual blocks of color. And each block is one solid color. And when you make those small enough, the image looks really, really good. Well, this image right now is creating a number for each and every pixel to number the color. And basically what they do is they have a red, green, and a blue, 3 different color channels, and they assign a number between 0 and 255 to each one, and they have to record that for each and every pixel. I know this image didn't look very big, but there are thousands and thousands of pixels in just that image. So this creates quite a large file size. And actually this image isn't very big, but this is about 750 kilobytes, almost a megabyte for that small image. But I'm going to show you a JPEG image, which I bet you could not even tell the difference if you looked at it. So here's the original one again. This is the full resolution, and I just switched it to the JPEG. I bet you can't even tell. I know your TV isn't the best viewing medium, right? But even on my computer screen, I can't tell. And this image is 3.7 times smaller. This is about 200 kilobytes. And with JPEGs, you can actually adjust the quality level. So here's another JPEG that's even smaller file size. This one, I wrote these down, is 8 times smaller, and I still really can't tell the difference. Here's the next one. This one is 10 times smaller, and I'm starting to see just a little bit of choppiness, and it's not quite as good. I kept decreasing the quality, though. This one is actually 12 times smaller, and again, I'm seeing a little bit of quality go down here. And I did one more. This was the lowest quality setting I could choose to convert it to a JPEG. This one is 15 times smaller, and there are actually some issues with this one. I don't know if you can tell on your TV screen, but I'm going to zoom into it a little bit. You'll start seeing blocks of color. In fact, you'll see sort of strange squarish patterns in the image there. So this is what JPEG is doing. So how does this work? I mean, how is it creating a file that's a lot smaller but actually still looks pretty decent? They've done some clever things. First of all, what they do is they take this image and they cut it up into blocks of 8 by 8 pixels. So as a sample, I've drawn a grid over this image, and that's the idea. They break it up in lots of little tiny chunks. Here is one of those blocks. I've blown it up for you. This is 8 by 8, so that's 64 individual pixels. You can see the individual colors, and they will turn this into a matrix of numbers. So actually what they do is they split this to 3 channels, and they don't just use red, green, and blue. They found out it's actually more efficient to split one channel just for the brightness of each pixel, and then 2 other channels that control the color. So one thing they do, for example, is they've studied that the human eye is much more perceptive on the brightness variations than it is on the individual colors. So they can actually average out the colors a little bit. So for instance, they could say, well, we're just going to take the color for every 4 pixels. We'll kind of round them off that way. And you can actually make the file 50% smaller that way, and most people can't even detect it at all. But we'll retain most of the brightness information. So for each of those 3 channels, we'll have these separate grids of numbers controlling those. And I'll show you what it looks like. It's basically a matrix of 64 numbers, and each of those numbers represents one of the color or brightness values. But this still is a lot of information to encode. So after that, they take this matrix of numbers, and they change how this is expressed. And they use something fancy called the discrete cosine transform. I know it sounds fancy. You don't need to worry about what it is. I'll show you its equation, though, so it'll look official, right? So here's the equation for you. What this is doing is it is basically creating a different expression for that matrix. And what it does is it takes a whole bunch of different cosine graphs. Now, I've shown you, these are 3D cosine graphs, and there's 64 different possibilities. I'm showing you a sampling here. And basically what they do is they add different ones of these together to create that grid of numbers or the level of colors. So for instance, this one you see in the bottom right corner is very choppy up and down. That would represent a lot of color variation in one little block. Most of the blocks that's not necessary. So for example, up top you see ones that just have a little bit of change. I'll give you a 2D version. This is all 64 blocks here And the differences are measured in brightness, and you see in the upper left there's just a solid white, and then there's some look kind of striped, and there's some look almost like checkerboard. So the idea is you would look at the color variation and the brightness variation on your block, and you would just take the appropriate ones of these to add them together, and you'll create something very close to the original. So once they do this, you're going to create a new grid of numbers, and to make it even smaller file, this is already a more efficient way to express the color variations, but to make it an even smaller file, what they do is they divide the numbers by something larger to make them all smaller, and then they round them off. So it's almost like saying if you have numbers from 0 to 255, we're going to take them and cut them down to only go to, say, 0 to 30, and we're going to round off the extras. So what that does, it kind of makes the colors rounded off a little bit, and it makes fewer things to keep track of. But then they're even more clever, because if you look at this matrix, most of the numbers rounded off to 0. And in fact, there's some logic to this. In the upper left corner, you see a -26. That represents the average brightness level for this block. And the numbers you see after that are how far they vary from there. So rather than giving the level for every single one, you just say, hey, on the average, they're -26, and the next one's 3 down from there, and the next one's 6 down from there. You get a lot smaller number to keep track of. And then they have one last clever trick. See all those zeros? When they list it in the computer file, they don't bother to say 0, 0, 0, 0, 0 over and over. They just say, hey, there's 45 zeros at the end. And there's a computer way of saying, make 0 happen 45 times, which is a lot smaller than actually saying 0, 0, 0, 0, 0. So when all is said and done, you can actually get a JPEG image that's about 9 times smaller that will look very good. In fact, it would be hard to tell. If you stared at it really closely, you might be able to tell, but it would be hard to tell from the original image. So keep that in mind. Next time you open up an image, and I have one more sample with me, you double-click on an image. It's a stream of numbers in your computer. Your computer opens the stream of numbers. It runs some mathematical algorithms to reverse all those processes we just discussed, and then it comes up with an image like this. Now, this is the full-size one. This is the JPEG version. You probably couldn't even tell I changed it. This is 7.5 times smaller file. It looks just as good to me. Probably does to you on your TV screen. And just for comparison, I put a low quality JPEG version on here. This one is 16 times smaller, the file. It's a very small file. It probably still looks okay, but if I zoom into it, you will see some choppiness. In fact, if you look at the bird's feathers and the beak there, you will start seeing some weird patterns in the blocks it's formed. But still, it's not bad. And keep in mind, every time you look at images, your computer is taking these numbers and undoing all these processes with algorithms. And if it weren't, in fact, if you have a digital camera right now, it's likely that it saves in JPEG format. Most of them do by default. If it didn't, that little memory card you have in there would hold a handful of photos and not the hundreds or thousands that it actually does. So next time you open an image, keep this in mind. Underneath there, it's all numbers and math, just like movies on your computer and MP3s on your computer and your iPod and everything else. But we'll get to those another time. All right. So anyway, I hope you find that interesting. Next time you open up an image, keep all that in mind. Hey, it's Mathman Dan. We are driving around the northeast part of San Diego County. We're doing some filming around here, but now we are lost. Luckily though, I brought a GPS with me, and if I just push a few buttons on this thing, it's going to tell me exactly how to get home. So how does this thing work? I mean, I know that it has the maps programmed in it, so that's one thing, but the main reason this thing can work for me is it knows exactly where I am. Well, it turns out that this little device has to do a lot of math to make that happen. And you might have heard that it talks to satellites to get its location. Well, that's sort of true, but this thing's not sending a signal to the satellites and asking, hey, where am I? And then listening for the response. In fact, this thing doesn't transmit anything to the satellites. The truth is there are 24 satellites orbiting the globe, and they are all transmitting signals that this thing can listen to. But first, all those satellites have to be synchronized. So they all have atomic clocks. They're precisely synchronized to be the same time. And with some mathematical tricks, this thing can figure out what that exact time is, so it can synchronize itself also. Then each satellite transmits a signal of numbers generated by a formula. This is programmed with the same formulas, so it knows what numbers are coming down from each satellite at precisely what time. By looking at the time it actually gets the signal, it knows how long each signal took to reach it. Well, since the signals travel at the speed of light, it can then compute how far away each satellite is from it. Well, there's one big mathematical problem left. If you just know the distance from a bunch of satellites, how do you figure out where you are on the planet, and how many satellites does it take? Because it turns out one is not enough, and in fact 2 isn't enough either. So back in the studio, I'm going to talk to you about exactly what math this thing has to do with these distances to figure out how exactly where we're moving and where we are on the planet so they can send us home safely. So back in the studio, I'll show you the mathematical tricks. In the meantime, this thing's going to get us home. You know, there's tons of math that went into getting that satellite system, up and running in the sky up there. But we're going to concentrate today on what that little device has to do to figure this all out for us. And I don't know about you guys, but that thing has saved me many times because, I don't know, I think I'm directionally impaired. Anyway, I brought in my GPS. It's on my math cam here. So I'm going to show you, for one thing, it shows you what satellites it's actually monitoring. So here's a little map of where we are. I'm going to have it show me what satellites it's listening to. And you can see right now it's tracking 10 different satellites. And I mentioned when we were in the car there that 24 satellites are up in the sky. There's actually more than that. The system started with 24, but they have some extras for backups in case one of them fails, and they also have put some additional ones because the more they can get up there, then you get more information, you get redundant information that can help you get everything figured out quicker. But quite a bit of math this little guy has to do. First, a couple pictures though before I show you precisely what it's doing. Here's what a satellite looks like. That's an artist's rendition of roughly what they look like up in the sky. And also, this is a little animation of the satellites in separate orbits going around. And what I want you to watch is there's a spot on the Earth there in the middle, and these satellites are all in their own orbits, but it's made so that at any given time, at any point on the planet, you should be able to see at least 6 satellites. So, I mean, my GPS right now was getting 10, which is more than necessary. So one of the questions I asked was, how many do you need to actually make this happen? And well, you don't need 6, you don't need 10, you can get away with fewer than that, but 1 or 2 is not enough as well either. So I promised I would show you a little math on how the device figures out where you are. And keep in mind, the GPS that you hold in your hand cannot communicate with the satellites. It's not sending anything. It has to just listen and somehow figure it all out. So as I mentioned, there's streams of data coming down. They have their clocks synchronized. And basically what happens is the handheld you have figures out how long the signal takes to get to it from each satellite, and then it figures out the distances. So the remaining question is, if you just know distances from a bunch of satellites around you, how do you figure out where exactly you are? And there's a lot of computations going on with the math, but I'm just going to show you some pictures because it's a little easier to explain that way. So first of all, what I have here, I have a little animation I've designed. So the blue thing in the middle, that dot, that's representing not the Earth, that's the satellite. And the yellow dot is you. And so if you have one satellite and you have a distance that you know, that means you could be anywhere around that satellite the same distance. And we're working in 3D here. So anywhere around there, you could be somewhere. If you only had one satellite, that's the best it could do. It could say, hey, you're hovering around me somewhere. So what we can do is I'm going to turn on a sphere here. And we can say, all right, you would have to be on the surface of that sphere. So the center of the sphere is the satellite, and the sphere represents all the different places you could be because you can roam around here any of these distances. So just one satellite, all I would know is, hey, I'm on this surface somewhere, we don't really know exactly where yet. Well, what if you had 2 satellites? So what I'm going to do is imagine that you have a measurement from one satellite. That means you're stuck on a certain sphere, and if you have another satellite somewhere else, then you can visualize being on 2 different spheres because those are distances from 2 different centers. And now you think to yourself, okay, how could you be on both spheres at the same time? You would have to be on their intersection. So I'm going to show you their intersection in red. So you can see that little red stripe hopefully around the 2 spheres. That's a circle. Anytime you meet 2 spheres up, they're going to be intersecting in a circle. So if I turn the spheres off, what we have now is this red ring you see floating in the middle. You have to be on that ring somewhere. So 2 satellites tells you, hey, I'm on this ring somewhere, but that's still not enough to figure out where you are. What if we turn on a 3rd satellite? Okay, well now I can see that it's hitting the ring in 2 spots. So with 3 satellites, I actually have 2 different possible locations. So technically 3 satellites isn't even enough. You actually need 4 to pinpoint one precise location. So one last little illustration here. And now keep in mind, the device is not drawing these pictures like I am. The device is actually taking the equations of the 3 spheres, which it's doing, and it's solving a system basically and figuring out what points are in common of all the spheres and figuring out where you must be. So 4 satellites minimum to make this all happen. Remember, the system's designed so you can see at least 6, and the reason is extra satellites provide extra information. So one last illustration here. I have the Earth drawn, and we're going to imagine that you have satellites floating above you, and we're going to start turning on those spheres of where you could possibly be. So here's one, for instance, that would show you that on the surface of the Earth you're on some ring. Then let's turn on a second one. So now I can see that, well, I'd have to be on the intersection of those two things, and if you're on the surface of the Earth, then there's only a couple possibilities. Let's turn on a third one now. Now you can see that it's pinpointing a spot. I don't know if you can see my little pointer there. Right in the middle there, it looks like you're roughly in, I don't know, maybe about Tijuana, Mexico there. So that's 3 satellites. Now, if you consider the Earth itself as data, you can actually get away with 3. Because if you know you're on the surface of the Earth, then that's sort of counting as a sphere you have to be set on. That might not be true if you're out floating in space, right? And you can use GPSs anywhere. So if you don't account for the fact that, hey, I'm on the surface of the Earth or at a certain elevation, you really need 4 satellites to make it happen. And the reason 5 or 6 is even better is they can more quickly determine where you are, because unfortunately there are little errors that creep in, and your handheld GPS has to adjust for those. So really, the more satellites it gets, the better. So why would there be errors? I mean, these things are very accurate if you look at them. They get you within, I don't know, like a yard of where you really are. Maybe it's not quite that good, but I mean, they're very, very accurate. Well, the thing is, these signals, as I mentioned, are coming down at the speed of light. So try and imagine that it's timing these, and it's counting the split seconds, probably several decimal places of a second here of how much time it takes. And if it's just slightly off, the speed of light is so fast that a very small error in time measurement creates a huge error in distance measurement. And if your distance is off, then your calculations are going to come out and give you the wrong location. So by taking several different satellites and looking at all of them where they could possibly overlap and converge, they can actually adjust for errors. And that's also, by the way, how they adjust for making the times all synchronized, because if the times are all off, then it's all screwed up too. So anyway, very complicated process, but just think about all the math that little thing's doing. Next time you're driving around, is taking it for granted that, by sheer magic, it tells you where you're going, right? So today we actually have a little bit of mathematics in music. It turns out there is a lot of tie-in between mathematics and music. And I don't know if it's a coincidence or not, but a lot of mathematicians actually play musical instruments. There seems to be some correlation there. So to set the stage, and I will come back with some math after this, for a one-time only appearance, we assembled the official College Math Line band. We formed a band of only crew members of this program who just happen to be musicians. We got us all together one day and filmed an official College Math Line song for you. And the name of our band, of course, was Brutal Equation. So we'll come back to some math after this, all right? This is just to set the scenario for it. So enjoy the one-time recording of Brutal Equation, then we'll be back.
And algebra has got you down, and calculus got you fall on the ground. Was the head and the water drown? That math man dad help you out. Math man dad, he's the man. He's gonna make you understand. Math man dad, he's the man. He's gonna make you understand. With trigonometry, your mind wanna flow. Think you forgot everything that you know. Instead of kicking the wall and breaking your toe, tune into Math Dad Show. Math man dad, he's the man. He's gonna make you understand. Math man dad, he's the man. He's gonna make you understand. Plus equals.
I feel so honored. All right, well, that was the premiere. Well, not quite the premiere. That was the one-time recording of Brutal Equation. So it is appropriate that we're playing some music on the program. There's a lot of math and music, and it would take me several hours at least to go over all of it. But I picked one particular place to show you today, and that is about the sound itself. So I have on my computer here a virtual piano keyboard. And this is a standard piano keyboard here. I'm going to play a couple notes here. And the thing is, every time you play a different note, of course, you hear a different tone. And what you might not realize is these tones are completely determined by mathematics. Basically what's happening when I push this on a real piano is the piano there's a hammer that hits a string, and it creates vibrations. Your ears turn those vibrations into tones. Those vibrations are based completely on trigonometric functions. So I have just this very simple example to show you. This is a sample sine wave. And basically, if I change the equation a little bit, I can both shrink or stretch the period you would call it in a trig class, but it's often called the frequency. The frequency is the number of cycles per second. So this graph really represents vibrations through the air. And for instance, if you do shorter cycles or higher frequency, it corresponds to higher tones on the piano or any other instrument. And if you do lower frequencies or wider cycles, it corresponds to lower notes. So if you look back at my piano here for a second, this note right here is an, oh, sorry, not that one, this one is an A. And this A is exactly 440 cycles per second, or hertz as they call it, H-E-R-T-Z. So the other notes of all these different kinds of frequencies, and in fact I printed out, I'll show you here, I printed out a sample piano. This is 1 octave here. So you see the letters on the bottom. If you're not familiar with music, they always letter the keys. So C is often the nice starting point. So this is a 1 octave from C to a higher C. And you can see all these crazy numbers on there. Those are the frequencies. So if I tilt this for you so you can read the numbers a little easier, hold on, get you there you go. These are all the frequencies, and most of them look kind of crazy, right? But the first C and the second C here, I want you to notice something. I'll go back to the piano here for a minute, and we're going to play those together. So here's the first C, this is called middle C, and here's the higher one. And if you play these together, it actually sounds good to the ears. In fact, those are considered the same note, just one higher than the other, so we call it an octave. Well, why are they considered the same note, or why do they sound harmonious to our ears? It all has to do with their frequencies. In fact, the higher one I played you was exactly double the frequency of the lower one. And if you look back at my numbers here, I know the numbers aren't the nicest, but if you look at the number for C here, it's 261 and some change. And then the next C down was 523 and a little extra. The 523 is exactly double that first C you saw, the middle C. So this creates sounds that are good to us. If I look at it on a graph, this is a picture of, here you go, these are double frequency sine waves. So this is what would be happening with those 2 C's, for example. If you can see the blue curve, the red curve does twice as many cycles in the same amount of time. So after 2 cycles of the red curve, they're lined up again. Well, this is the key to why they sound good to our ears. Now, if you go back and look at the piano again, let me show you this one here. These little guys on the right, those are the black keys on a piano. If you play just the white keys, I'll do it on the piano here, you hear the traditional, the do, re, mi scale thing. So I'm not going to sing it because you don't want to hear that, but that's a typical scale. Now, that is not playing equally spaced notes. I know that sounds nice and smooth, but if you want to play equally spaced notes, you have to play the black keys as well. It's not going to sound quite as nice, but this is playing all the notes from one C to the next that do exist on a piano. So starting with middle C, it would sound like this. If you counted, that was 12 steps from one C to the next. So at some point they had to decide, in history, the instruments have gone through different progressions, they decided to cut 1 octave into 12 equal pieces. So there's a couple things to figure out there. One, we're going to see where all these crazy numbers came from. So we need to figure out how to divide things nicely up into 12s. And the key is, it's not by adding the frequencies over and over, because remember, to make sounds that are nice, an octave especially, you would double the frequency. So the question is, how do we get from 261 down to 523 here, which is a doubling? How do you make 12 steps to do that, all evenly spaced? And the key is, it's in terms of multiplication, not in terms of adding. So basically, here's what we have to have happen. If you had one tone, we need to multiply it by something 12 times. Well, another way to say that is a 12th power. So I want to take some multiplier, I'll call it x, and we're going to do 12 powers of it, and we want to get 2. That would be a doubling of the frequency. So what is that magic number? Well, if you solve for x, x would of course be the 12th root of 2. Now that is not the nicest number in the world. In fact, it's about, I did it on a calculator, it's about 1.06. So that's rounded, but if you were to multiply each of these frequencies you see on this list by 1.06, you would get to the next frequency. Okay, so that explains maybe these strange frequency numbers you're seeing. In fact, the only nice one you see on the whole list is that 440 sitting at A, right? This one right here, that's the only nice one. The others are kind of weird. So why did they pick these weird frequencies? I mean, whoever, it was actually in the 1930s, I believe, that they standardized all this. Well, the key here is that the notes that sound good to your ears, all of it has to do with the ratios that these frequencies make. And it turns out the nicer the ratio, in a sense, the the nicer the sound to your ears. So back to the piano for a second. If I play a C right here, and I make 4 jumps up to a note, so this is a 5-note difference basically. This is a G. Sorry, this is a C, D, E, F. Yeah, it is a G. That is called a perfect fifth, and that sounds pretty good to our ears. Whereas if I play 2 notes right next to each other, that doesn't sound so good. So how come, and who decides what notes sound good together and what notes don't? Well, if you go back and look at our frequencies, the perfect fifth I mentioned, let's see where that is. That would be from this guy here, C, down to G. So if we look at these measurements, the 261 frequency down to a 391 frequency, you could take a ratio of that. You can go on a calculator, divide the larger number by the smaller, and you will get a ratio of, it's very, very close, almost exactly 1.5. So that's a ratio of 3 to 2. So we can say 3 to 2 ratio. So if you look at a graph, so again I have some sine waves here. If you look at a graph of these guys, this is a 2 to 3 ratio, and you can see that they are out of phase in a sense, but they line up fairly quickly. So when the blue one does 2 cycles and the red one does 3, they line up again. So again, the key is if it doesn't take too many cycles to line up, it will sound good to your ears. So some other ones that sound good, if you want to look at our picture again, 1 and 4, so that's a perfect fourth, so that would be C to F. That's a step of 3. That also makes a nice ratio. So this one right here makes a ratio of approximately, and this is round a little bit, but this is approximately 4/3. That's a decent ratio. If you go see the third note down, that's about 5/4. So they were really looking at these ratios. If you can make ratios out of fairly small numbers, they tend to sound good to the ears. Remember those 2 I played for you that sounded bad right next to each other? That was a ratio of 16 to 15. Not such a good ratio, higher numbers there, it doesn't sound so good. There's another bad one if you go all the way to the end to this number at the end, this letter rather, B, this key. It's a ratio of 15/8. I'll play it for you, it doesn't sound all that great. So this would be these 2. Not very pleasing, right? So the whole key is notes sound good together when their ratios are nice, formed of nice small numbers. It still doesn't quite answer the question, why did they pick 12 notes between the octaves? And you know, almost all of Western music, any instrument, any recording you buy is based on these same 12 tones in different octaves. Well, it turns out if you divide it into 12 pieces, if you go back and look at all those crazy numbers we got off of our keyboard here, the more of the ratios turn out good. So these ratios we saw are about 3 to 2, about 5 to 4. They're not exact, but they're so close that to our ears they are good enough to sound nice. And there's a lot of them that are possible out of 12 tones. If you split the octave into 10 parts, for example, it doesn't sound as good. There's just not as many good combinations, and there are more bad combinations. So it didn't turn out to be a very practical choice. A couple interesting things. There are other countries around the world who use completely different tunings. They have different numbers of steps between their octaves, and the music sounds different. Might even sound weird to us because we're not used to it. They probably think our scales sound weird. Also, if you hunt around on the internet, you can actually find examples where people have taken scales and split them into not 12 chunks, but like 30 or 40. And if you go high enough, you can actually get more precise, good-sounding pairings of tones. You just get a lot more bad ones as well. And besides, can you imagine if a piano had 40 keys between every octave? It'd have to be humongous. So that wouldn't be very practical.